Welcome to the sixth lecture video for Physics 4B. We are wrapping up thermodynamics in this lecture set. We will start with a brief review of what we have covered in the last four lectures, and then work through four exam type questions named Kinetic Theory of Gas, Carnot Pump/Engine, First Law, and Thermodynamic Processes. This is it. Other than occasional use of some thermal physics concepts, such as specific heat, when needed in the course of answering electricity or circuit problems, we won't return to thermodynamics for the remainder of this course. Also, depending on the semester, we may have already skipped to the electricity and magnetism right after lecture 2, returning to lectures 3 through 6, this one, at the end of the semester. And this approach works out because the thermodynamics processes we covered in lectures 3 and on are quite independent of the rest of the course topics. We start with a condensed review of what we have covered in chapters 1 through 4, plus additional coverage of heat engine cycles in the last few weeks. In chapter 1, we covered what might be considered background material, addressing several thermal physics topics that may have been covered in a previous science class or a chemistry class, including thermal expansion, specific heat capacity, changes in phases of matter, and heat transfers that take place with phase changes. Calorimetry, problem solving in particular, could require that you carefully write down the heat balance equations. What we covered in chapter 2 still had a great deal of overlap with what you may have covered in a chemistry class. We covered the ideal gas law, whose main usefulness you saw when we looked at thermodynamic processes, because it related thermodynamic quantities, pressure, volume, and temperature together. We also looked at heat capacity of an ideal gas and the relationship between temperature and average kinetic energy of particles through the equipartition theorem. In lecture, we looked at how we can use the kinetic theory of gas to derive the ideal gas law from the first principles. Thermodynamics started with chapter 3 when we looked at the mechanics involved in thermodynamic processes through the first law of thermodynamics. First law of thermodynamics relates to three key quantities involved in any thermodynamic process: the change of internal energy, heat transfer, and work done by the system. Mind you, the sign convention for the work we use in this physics class may be different from what you have seen in a chemistry class, because we are talking about work done by the system, not work done on the system. We introduced the four named thermodynamic processes: isothermal, adiabatic, isobaric, and isochoric processes. And I demonstrated a problem-solving approach in thermodynamics, where you diagram the process on a PV diagram, calculating the work done as the area under the curve, and using the ideal gas law, along with equipartition theorem relating temperature to internal energy, gas law, and the first law to find the necessary quantities. There are other useful things from chapter 3, such as the adiabatic relationship, which follows from the increase in the internal energy when work is done on the gas without heat outflow. This effect was demonstrated with the fire syringe. And we spent some time analyzing heat engine cycles in detail. While the process of this analysis can be very tedious, I encourage you to review by trying out each engine cycle analysis on your own. Oh, and as a treat, here's a video of a working lecture demo of a Stirling engine. Finally, we wrapped up our coverage of thermodynamics with chapter 4, where we introduced the new state variable entropy and gave several different statements of the second law of thermodynamics. So, in very broad strokes, that was our coverage of thermodynamics. I encourage you to review/rewatch the lecture videos for any big sections in which you can't remember the details, and to really practice analyzing thermodynamic processes illustrated on a PV diagram, either as part of a heat engine cycle or on its own. There are many homework help videos that show sample analysis of thermodynamic processes. And we'll start. I haven't seen this question actually. The next part I've had to look at the question, but this part I haven't seen. Okay. So kinetic theory of gas. Okay. In kinetic theory of gas, we treat gas as a collection of real interact particles, right? Ideal gas moving at some speed. So we might be referring to some sort of VRMS. Colliding with the walls and with each other, consider helium gas at a temperature of that. Okay, so we are given some temperature, and we are given mass of the helium gas. At the temperature on average, how fast are helium gas particles? So you are allowed to use your textbook. So it's open book. Textbook is not outside the help. So if you feel like referring the textbook will help you answer, then great, do. One thing I'll tell you is that that's one of the reasons we have the time limit, because within 20 minutes, if you're having to kind of flip through textbook a lot, you will probably run out of time. So an ideal student should know, as you are reading this, realize that, it's a question involving equipartition theorem, which in particular mentions. So I guess the way equipartition theorem goes is for every quadratic degree of freedom, so degree of freedom d, there is energy, average energy, d over 2 kBt. So that's the rough statement of the equipartition theorem. So for helium gas particles, it's monatomic. So the only degrees of freedom it has are the 3 translational degrees of freedom. So for a single helium particle, its average kinetic energy, average translational kinetic energy would be 3 over 2 kBt. And I think that's it, because it's asking for average speed of helium gas particles. So I don't have to consider how many particles there are. I'm just considering one particle. And to relate from here to the actual speed, you would express, using the concept of RMS speed, you would say this average kinetic energy is 1/2 mass of the particle times the RMS speed squared. So solve this expression for the RMS speed. I'm gonna just do that in my head, double check me, make sure I didn't make any algebra mistakes. And then in the interest of time, I'm gonna plug in numbers in Wolfram alpha, because that makes things easier. Easier with the unit conversion. And also Wolfram alpha can just look up Boltzmann constant. I don't have to look it up. And the temperature, I had 285 Kelvin. 285 Kelvin divided by mass of the helium. I'll use the value they give us, 7 times 10 to the minus 27. 7e minus 27 kilogram. So that should give me some number in meters per second. Pretty high usually, yeah. 1300 meters per second. So 1300 meters per second. Yeah. And I'll just write This is equal to 1300 meters per second, Wolfram alpha. And by the way, Wolfram alpha is always allowed. As far as this class is concerned, it's a sophisticated calculator. So it's not considered to be outside the help, even during kind assessment. It's just a calculator. Suppose that this helium gas is in the volume of that. If the density of the helium gas is that, estimate the rate of collisions between the... Yeah, so think if you recall my the kinetic theory of gas lecture, that might help you. Otherwise, you'll have to try to kind of reproduce argument within this timed assessment time limit, which can be challenging. But do your best. I certainly don't recommend watching the lecture during the timed assessment because there won't be enough time. So this is what I'm thinking. I have some helium gas particles in the box. So let's say it's moving at some speed. And for simplicity's sake, let's say it's moving at VRMS. There's gonna be some error if I do that, but I'm just trying to get an order of magnitude estimate. So moving at the speed, I can think of like an example helium particle going from one end to the other end. So it's gonna be traveling some distance L. I have some idea of its speed, some idea of its distance. So the time between collisions for this one particle is going to be that distance divided by VRMS. That'll give me time for one particle. So for the total, it's a time for one particle. So if I want the rate of collision, it's going to be reciprocal of that time. So, if it takes 1 second, then I'll have 1 collision per second. If it takes, 0.1 second, then I'll have 10 collisions per second. So all of this, what I'm doing is for single particle. So to get the number that they are expecting, where they've already given me the density of the helium gas particles, I'll have to take this rate that I got and just multiply that with the total number of particles. And from the given information, I would figure out, okay, the number of particles is the density, this number. I'm gonna use a lowercase n for number density, times the volume, which they gave us, 1.3 meter cubed. So I think that's everything. So I think I can do the rest in Wolfram alpha. So I'll have, let's see, I want to have the numbers on the screen. So I need my n, so number density, 2.9 times 10 to the 25 atoms, which is not a unit, but meter to divide by meter cubed, that is a unit, so that's the density, times the volume, 1.3 meter cubed. Oops, it might misunderstand the m, so let me just spell out meter. So that's the number of particles, and I say multiply that to this reciprocal. So it would be VRMS over L. So VRMS, I'm just going to use the VRMS I calculated above, not repeat the work that I've already done. Divided by the length of a cube. Oh, so I'm not given length of a cube, but since I know it's a cube of this volume, so I can take the volume, 1.3 meter cubed, and take a cube root, which I guess I have to do that by raising it to a power of a third. So yeah, let's see. So the unit I get should be some unitless quantity per second. That would be collisions per second. Yeah, something per second. This seems high, 4.44, so 4.5 times 10 to the 28 meter, whatever, per second. Yeah, 4.5 times 10 to the power of 28 per second. Yeah, I guess that's right. I don't know. With these really microscopic numbers, I don't have a good number sense. So that's the number of atoms. I don't know. It's at least not minus 10 to the 10 to the minus 28. So I think that's fine. And again, one caveat: the way I just estimated this, it'll definitely have some factor, kind of the factor of error that's like within a factor of 2 or 3. Because really you have to think about its motion in 3 dimensions. So you have to think about the component of velocity along one of the axes, which I haven't done. But I think I set the grading for this question generously enough that if you are off by a factor of 2, the system should still grade it as correct. So okay, Percy, with each collision on average, how much? Oh, we're not done. Okay, we're still on the same topic. So with each impulse, well, so this is the scenario I'm thinking of. Particle comes in with some speed, again, with acknowledging some error. I'm going to say that's VRMS. It's going to collide and reflect back. So the particle that's coming in, it has some initial momentum. That's going to be, let's say, plus m VRMS. The particle that's reflected out, it has a final momentum, which is going to be minus m HVRMS. I'm using plus and minus to indicate the directions. So when you take the difference in the momentum, that's going to be basically twice of this incident magnitude. And it's asking for average impulse. Oh yeah, so I think this is the impulse, if you remember the definition of impulse from physics 4a. So guess I'll just plug in numbers in Wolfram alpha. So I have 2 times. I'll reuse this VRMS that we calculated above, and then I need the mass of the helium atom, which I had above. 7 times 10 to the power of minus 27 kilogram. And impulse doesn't have its own unit. Impulse of Newton times a second. So actually, if you want to confirm it, here it is, Newton second. It is one of the acceptable units for impulse. 1.82 times 10 to the minus 23. 1.82 times 10 to the minus 23 in the basic SI units. And yeah, part D is really the thing that I hope you are kind of working through the assessment and you have enough time to think through. I hope for me something like this is the eureka moment that explains the ideal gas law. So it forms the basis of derivation. Explain below how each of the following quantity change or don't change if Wait, what? Oh no, so never mind. Part D doesn't actually do that. So there's a missing part here, which you will see it in the lecture. You can take this impulse and multiply that with the rate of collision. That'll give basically impulse change on the wall per time, and change of impulse per time is our definition of force. So you get the force on the wall. From that you can calculate the pressure, so you get an expression for pressure, which you can rewrite into the form for ideal gas law. I guess I'm not asking you to do that. That's done in the lecture. Sorry, this is not very impressive. But let me answer this. So explain how each of the following quantities change or don't change if helium is replaced. The only thing that's changing is the mass. So the speed of the gas particle, looking back up, VRMS here, it does depend on the mass of the particle. So VRMS will change, decrease by square rooted factor. So rate of collision with the wall, I guess that'll change, because when you look at rate of collision, so let me just write this out explicitly. That was VRMS over L. So if a VRMS decreased, then yeah, rate will decrease. So we'll say rate of collision with the wall decreases by the same factor as VRMS. Impulse on the wall per collision. I think that actually increases. So impulse is this. 2 times mass of the particle times the VRMS. And here you do have to be a little bit careful, because let me just spell it out. Looking at so we've argued how VRMS is proportional to to 1 over square root of mass. So if mass quadruples, then VRMS goes down by a factor of 2. So when you look at this delta P is equal to 2 times mass times VRMS, you have to do a bit of what we call scaling argument. So you recognize that this is linear with m, because it's m, it's proportional to m. This is VRMS, it's proportional to, again, 1 over square root of m. So when you do scaling argument, you are multiplying this factor with this factor. So overall factor is square root of m. So you have a factor that increases with increasing m, another factor that decreases with the increasing m, and their combination isn't that nothing changes. And something does end up changing, and the change of momentum that's proportional to square root of m. So the answer here should be the change of the impulse per collision increases. Scaling as square root of m. Finally, pressure on the wall by the gas. Oh yeah, so this is the thing. So in working out the pressure, so what you will have seen in the lecture and what you could have done here is, so pressure is force per area. And force in mechanics is defined as change of the rate of change of momentum. So you have 1 over area, which is going to be constant for the purpose of our description. So you'll have this delta P times the rate of collision. So this is the change of momentum per collision multiplied by collisions per second. So times the rate. And this portion is equal to the force. So you have an expression for pressure that goes as this. And we've so far argued that the rate of collision decreases by this square rooted factor. So the rate goes as 1 over, it scales as 1 over square root of m. And the change of momentum, as we argued above, it scales as a square root of m. And when you multiply these two, now there's no scaling with respect to m. So the pressure on the wall by the gas does not change. And which you might have expected if you think through the ideal gas law. Ideal gas law actually doesn't depend on the properties of the gas. You can have a super heavy particles, and as long as they're not really interacting with each other, the mass of the particle doesn't matter. And this is a really beautiful, wonderful cancellation that, from the chemistry perspective, you would never see, because you simply see that, oh, it doesn't change, so it must not matter at all. But the way in which it doesn't depend, it's a kind of a beautiful coincidence when you work through the physical kinetic theory of gas. So, okay, I'm just attaching work, and my recommendation to you. So I happen to be doing this because I worked through the question relatively early, so I had some extra time. My recommendation to you is don't worry about attaching work while you are working through within the time limit. That's totally unnecessary. And in fact, I prefer to see a more organized work than what I'm going to be attaching. So if you actually take the time to organize your work and then attach it, I would actually prefer that over what I'm doing right now. I'm doing what I'm doing right now because, I got bored. I got bored listening to myself talk. So let me just finish doing this, and then I'll finish demonstrating the logistics, mechanics of this timed assessment. Some of the oddities you might have to watch out. Okay, put in all the work. Yeah. So, and I answered everything. And the way some of the timed assessment in these classes work, especially with the answer boxes that look like this, some of them are auto-graded. And so when I submit, I will probably receive some kind of a score. So let's submit and see. If I answered any some of these right, I should get non-zero score. I guess it's not telling me the result yet. All right, that's fine. So after I've submitted, this is now outside the time limit, I can actually edit it here. I can delete it if I want to. I can do other stuff to it. And now this isn't the only place where you can change it. So if I do, let's say there's a mistake in the work that I find later, and I only discover it after I've already done save work and continue. I can still, find and change it. Oh yeah, so this must mean I got 3 of the answer boxes right, and the very last one, because it's an essay box, it doesn't auto grade. So let me do review work. And I think when you do review work, yeah, it doesn't tell which ones you got right. And the reason you see score at all is because of the operation of LTI. The way LTI works, I can't prevent you from seeing your score. So I'm just guessing based on this is 3 out of 4, that I had 1, 2, 3, 4 boxes. These 3, I know enough to figure, I probably did it correctly. So I got credit for this, and I didn't get any credit for this because this is manually graded. So one thing that I guess I would tell you, not to worry yourself with, is imagine, you did all this and you got 0. And don't think that's terrible. One, whatever auto-graded score you have, it's not your final score. I am going to be reviewing all the freeform timed assessments and grade it manually. And when I grade it, I actually look at your work. So like you could have gotten 10 out of 10, but let's say you didn't attach any work. I'm going to be deducting points. But let's say you got 0 out of 10. Maybe you made some factor of 10, power of 10 error, maybe. Then as I review your work, I can see clearly where you made the mistakes. Then I'll be making up that point. So until you see me having graded your work manually, don't pay any attention to the scores you see, because it could go up, it could go down. Yeah. So let me just do this one, just because it's more of a kind of standard strategy vibe, in the sense that there's a more kind of fixed set of steps that I out to follow. Versus sometimes with the kinetic theory of guess, it can be a little bit unpredictable what it is I might have asked. Um, so so yeah, let's do this one. So actually, I should have this ready. So I'm going to try to do this as a demonstration, as sort of the both to demonstrate the logistics of how this works, and to kind of show at least one of the questions that would one potential question that might look like what you would see. So I'm gonna start, and 20 minutes. It's a fairly tight amount of time, even for me. So within the 20 minutes, I might not be explaining a lot. I'll just get focused on just producing the answers, and if necessary, I will come back and fill in some of the gaps after those 20 minutes. 20 minutes is a tight amount of time. Like even me, I don't have a lot of time to waste explaining. So I'll start. I look at the clock so that I know what to watch out for, and go. And same rules as multiple choice, open book, no outside help, and so on. The one thing that's different, it's only one attempt. Because things that's manually graded, like multiple attempts, are annoying to deal with. Annoying for me, probably not for you. Annoying for me. Okay. And actually, one issue I've had in the past, I used to give 2 attempts, but then I would say that whenever people got a difficult question, they wouldn't even attempt it. They would just retry to get an easier question. When I saw that, I said, "Oh, I can't. I gotta limit it to 1 attempt." Okay, I got Carnot cycle here. Yeah. A, B, C, D occur isothermally, answer below relating to the Carnot cycle. Okay, might be one of the easier questions. Yeah, good. I think I understand the question. In the case of a reversible Carnot heat engine, its efficiency takes the simple form of that. In the space below, briefly explain or how this comes about. How does the okay, so I think I've demonstrated this in the lecture. I actually did it backward. We actually kind of started out with the efficiency of a heat engine in general is given by efficiency is equal to work done divided by the heat transfer at the high temperature. Now this can be simplified into this form: QH minus QL divided by QH, using first law to say the work done on a cycle is QH minus QL, or conservation of energy. And in the lecture, we did it the other way, meaning we were trying to introduce the idea of entropy. And in order to introduce entropy, we are looking for some kind of state function, and that's how we went. The kind of the answer here would be to go the other way, which is we already know for reversible processes, we have that change of entropy is equal to amount of heat transfer divided by the temperature. And in the case of Carnot cycle, heat transfer happens only along isotherms. Uh, Isotherms up here and down here. It's really nice because along the adiabatics, no heat transfer, so no change of entropy. So, so we can say that the change of entropy at the high thermal reservoir where heat's coming in, so entropy is increasing, you have plus QH over TH. And also, we can say the change of entropy at low temperature reservoir along this isotherm. Now, heat is leaving the system, so change of entropy is negative there. The engine is becoming less disordered. Is QL divided by TL. And because this is, well, not because it's reversible, but because this is a cyclic process, delta SH plus delta SL is equal to 0. Meaning QH over TH is equal to QL over TL. This is where it's nice to notice this thing. So this expression for efficiency, you can express it in terms of ratios of heat transfers. So if you imagine dividing by QH, both the top and bottom, numerator and denominator, then on the numerator, after distributing it through, it becomes 1 minus QL over QH. And on the denominator, it becomes 1 up. So there's no denominator anymore. So I have a 1 minus QL over QH as an equivalent expression for the efficiency of any engine. And now once we say efficiency of a Carnot heat engine, then we can use this expression that we derived above. That or actually I need to go one more step. Just moving them around so that QL is on that side and TH is on this side. Then it's gonna be QH over QL is equal to TH over TL. This ratio is reciprocal of that. So I can put in reciprocal of this in that place. So it's 1 minus TL over TH. And that is the expression for the Carnot cycle. Oh, and let me just make sure. Yeah, T1 is greater, so I'll just say TH is my T1 there, and TL is the T2 there. Yeah. So that's it. I guess yeah. Question like this one, there wouldn't be additional work because you are explaining things in words. So yeah, what you submit here will be work and answer. Um, compared to real world heat engine cycles, for example, yeah, diesel cycle, isotherm ensures that Carnot engine will be more efficient than the other. I'll briefly explain below. So yeah, so I'm just gonna type everything in here. So these are easy to answer using entropies. So because heat engines operate on cycle, change of entropy net is zero over that cycle. Uh, entro- uh, sorry, Entropy is a state function. I also irrationally don't like the word state function, like closed system, isolated system, state function. If you want to see me wins, like those are the words to use. Sorry, I just don't like those words. I don't have a good reason why. I just don't like them. Um, Over the cycle, meaning whatever increase in entropy through heat input, um, delta S is positive with the Q high input at high temperature reservoir has to be disposed of um, through a decrease of entropy that takes place. Uh, Extra comma. Takes place with heat output delta S um, is negative with a QL output at low temperature reservoir. So we want the heat input to take place at the highest possible temperature, minimizes delta S equal to Q over T. If T is high, that means delta S is small. And we want the heat output to take place at the lowest possible temperature. Maximizes absolute value of delta S um, Q over T. So when this thing is negative, we want its magnitude to be as large as we can make it. So that's what we want to make things, make the heat engine as theoretically efficient as possible. Carnot heat engine cycle accomplishes that because all the heat transfer occurs along isotherms, representing the highest possible temperature and the lowest possible temperature. For all other heat engine cycles, those that basically do not connect the two isotherms with the two adiabatic curves. Because if they do, they are Carnot cycles. If they don't, it's something else. um, Heat transfer occurs range of um, over a range of temperatures. So whenever heat input occurs at a temperature lower than the highest possible, extra entropy increase occurs, reducing efficiency. And whenever heat output occurs at a temperature greater than the lowest possible, um, additional heat output is necessary to get rid of the entropy increase from earlier, uh, also reducing efficiency. So so uh, so the arrangement of isothermal processes and adiabatic processes, adiabatic processes that ensure no heat transfer at temperatures, at non-ideal temperatures, non-ideal temperatures, ensures the most efficiency achievable given the two extreme, given the two thermal reservoirs available. I think, yeah, let's leave that there. And 8 minutes. Do I need to go faster? Possibly. Yeah. Okay. The cycle can be reversed to form a pump or refrigerator cycle. Coefficient given by that, right? Coefficient given by that. Okay. Um. Oh. To the difference comes down to a difference of what we want. In general, efficiency or coefficient of performance is the ratio what we want divided by what we pay. Uh, for heat pump, what we want is QH, heat input into the high temperature reservoir. So the coefficient of performance for heat pump is QH divided by work. Uh, and going through um, the usual derivation gives the expressions shown. For um, refrigerator, what we want is QL, that is heat removed from the low temperature reservoir. So coefficient of performance for refrigerator is equal to QL over W. And going through the usual derivation gives the expressions shown. So that's really the difference. I mean, there isn't any other profound difference than that. It's the goal for those two devices are different. Okay, question 6. I think this is actually one of the easier questions. So if you get this question, you are lucky on two counts. One, you got the easier question. Two, you see me do it. So this one is probably the one tricky question because a lot of times people think so consider real Carnot heat pump that involves irreversible solid heat, how this change resulted in reduced the coefficient performance for the heat pump. Explain words as you include the. Oh wait, this isn't tricky. I used to have a different version of the question that was tricky, but it wasn't this one. So let me do the text version, and I'll draw the PV diagram. I think I have enough time to do that if I don't waste so much time and exceed my 5 minutes. So the explanation for the would be so just considering the coefficient of performance for a heat pump in general is the heat transfer into the high temperature reservoir divided by work done. Right? Or um, yeah. So for um, for a real Carnot pump involving irreversible, so this, um, which in case of uh, reversible Carnot heat pump is equal to QH over QH minus QL. This is not the irreversible part. The irreversible part is where I change Q's into T's. TH divided by TH minus TL. Uh, for a real Carnot pump involving irreversible transfer of heat, the achievable coefficient of performance is lower. Guess this is the I think I have the time 3 minutes. Yeah, so it's a better drawn on figure than explained in words. Imagine this PV diagram, and let's say you have access to two isotherms, the high temperature reservoir isotherm and the low temperature reservoir isotherm. So your Carnot pump is moving along the moving between the points here. So I'm trying to do it the opposite. So for a heat pump, you would, let's say, start from here, go through isothermal contraction, doing the outside doing work on the system, and then it'll go undergo adiabatic expansion, expanding, and then it'll do isothermal expansion, expanding, and then adiabatic compression, bringing it back to the original point. So, um, so your thermal reservoir temperatures are the same as your engine temperatures. When you have irreversible transfer of heat, what that forces you to do is instead of the engine being right at the temperature of the thermal reservoir, the at this point while you are trying, so in this step heat is being transferred out of your engine, or sorry, pump. I think that's right. Outside is doing work. Yeah, heat is being transferred out. So in order for this to happen naturally, meaning irreversibly, then you need to have your engine that's at a temperature higher than your thermal reservoir, so that your engine pump can bleed the heat into the reservoir. Let me check time. Okay, 2 minutes. And on the other side, while you are doing while the heat pump is doing work on the system, it's on this part the heat is entering the engine, so the pump. So the temperature here has to be lower. So with the irreversible processes, what you are forced to do, uh, because with the irreversible transfer of heat, the temperature of heat pump TH prime is greater than TH, and the temperature of heat pump TL prime, is lower than TL. And with these inequalities accounted for, the real coefficient of performance, it's less than the ideal coefficient of performance. I skipped some steps because I have 1 minute left. Let's give it a try. So I've done this just so that I don't get kicked out before I put in all the part that will give me full credit. And I think I'm still gonna get kicked out. So I'm gonna do the rest on the work here. Let's see. I have Kp is equal to Th over Th minus Tl. So I think it's easiest if I divide by Th, so that I have 1 over 1 minus TL divided by Th. So this is the expression I have for the ideal Carnot heat pump. So for the non-ideal Carnot heat pump, I can actually use the same expression more or less. What I have to change is what temperatures I use. Instead of my thermal reservoir temperatures, I have to use the heat engine temperatures or heat pump temperatures. So 1 minus TL prime over TH prime. So I'm trying to compare these two numbers. And so comparing them, let's see. I've said, so from this picture here, TL prime is less than TL, and TH prime is greater than TH. So the ratio, so the numerator is less and the denominator is greater. Yeah, so I can say TL prime over TH prime is less than TL over TH. Both of these effects are working in the same direction. So this being less, the whole this one, did I mean to do that? 1 minus this is greater than 1 minus TL over TH. And this denominator being greater than what's here, that means Kp prime is less than Kp. So that's the argument. But yeah, that part, people seeing it for the first time, um, like, yeah, if you didn't immediately get it, that's fine. I think I spent some time thinking through it, and what you're seeing me in this session is me just remembering that argument I went through long time ago. So let me just attach this for part D. Uh, part D. Yeah, and that question used to be a little bit more tricky. I was asking like, is the coefficient of performance um, the realistic Carnot heat pump higher or lower? And the thing I was trying to trick people into saying is because the heat engine efficiency is lower, so my heat pump efficiency is higher, and it doesn't work that way. It's the thing about irreversibility. When you have one effect in one direction and you reverse it, you can't just do that. Because so actually, even in this picture, so for heat pump, I drew the one for the realistic engine this way. If it had been heat engine, the realistic heat engine would have actually looked like this. On this side, it would have to be lower, and on this side, it would have to be higher. So what the correction looks like for the realistic heat pump versus heat engine, it's not the same. That's sort of what being irreversible means. When you reverse it, you might be able to reverse it, but it wouldn't reverse exactly the same way. Yeah, so let's do part two, and add to the demos that I've done so far, and have more examples of me working at the heat engine stuff. That's really the reason we cover thermodynamics, even though many of you might have seen it in your chemistry classes. I think in chemistry classes they don't emphasize heat engine cycles as much as we do. So they care more about stuff like enthalpy and all that. I don't even use the word enthalpy except just now. So let's get started. I hope I don't get one of the two questions I've already done. That way I can, yeah, this is not one of the two questions I've done, I think. Yeah, the other one had some graph there that I don't have. So, all right. First law of thermodynamics gives a statement with the quantities involved. Yeah, yeah, all that. Imagine a monatomic ideal gas undergoes expansion. Oh, yeah. So let's sketch it out. That helps me think through the scenario and not make mistakes. So the first step, almost always in thinking and analyzing thermodynamic processes, is drawing a PV diagram to visualize the changes that are occurring. So I'm given that a gas is at some pressure, 105 kilopascal, and it's starting from some volume. Let me say 5 times 10 to the minus 4 meter cubed to 17, not to scale, 17 times 10 to the minus 4 meter cubed. And then it's not describing change of pressure, so, and it just says at a pressure, so this is probably the process. Good? So it says calculate the change in internal energy of the gas, heat transfer into the gas, and work done by the gas. Internal energy is easy. Let's make sure I know what type of gas. It said monatomic. And monatomic is important because that implies the internal energy is given by 3/2 NKBT. And I'm going to use this expression to replace out of ideal gas law, which says PV is equal to NKBT. So I can replace this NKBT with the left-hand side of the ideal gas law. So I can say the internal energy is equal to 3/2 PV. So, all right, I think I have all the numbers to plug in. That's the internal energy. So the change of internal energy is, change of this, change of delta PV. Here pressure remains the same, so it's going to be 3/2 P times change of volume. Let me do this in Wolfram alpha. Yeah, I think I have all the numbers. 3/2 times pressure, 105 kilopascal, times the change of volume, which would be 12e minus 4 meter cubed. I did a difference in my head. It's quicker. 189 joules. 189 joules. Good. Now Q, I can't quite calculate it directly. Really, for this process, referring to the first law, easiest thing to do is find internal energy change, work done, and from that calculate Q. I can say Q is equal to change of internal energy plus the work done by the gas. So let's calculate the work done by the gas. That's pretty easy in this case. It's basically area of this rectangle. Or, I guess this is work done by the gas, P times delta V. P is the height, delta V is the width. So here, in fact, I already have P times delta V, just get rid of 3/2. That's my work done, 126 joule. And heat transfer from this expression here is the sum of these two. Oh, I think I can do that in my head. 315. Hopefully I did it correctly. Considering the same initial conditions as in A, so let's copy this over. And I can reuse some of the stuff. This time it's B. If the expansion occurs isothermally, I don't think I can use a lot of the stuff. So let's do isothermal expansion. That actually gives me an easy answer for change of internal energy, because no change in temperature means no change of internal energy. And whatever I calculate for work, that's going to be amount of heat. So let's work that out. I think I can still keep a lot of the stuff. I just have to draw a new process that shows isothermal expansion. So isothermal expansion looks like 1 over x graph, because that's the curve that will keep the temperature the same. So it'll look something like this. So, this is almost 3 times the volume. So the pressure will have gone down by almost a factor of 3. I can calculate that. Or maybe I don't even have to calculate it. So I have a feeling I'm gonna make use of ideal gas law, so I'll keep it for now. Let me erase this part. So the work done here gets a little bit more complicated. I have to do an integral. The work done here is going to be integral from initial to final of the infinitesimal work done. So let me write that out. I have infinitesimal amount of work done, which is going to be at a given pressure times the infinitesimal volume change. And I'm going to integrate this from the initial state to the final state. From the initial volume to the final volume, which I conveniently have. So I'll just keep everything that way. Now, I do need a pressure as a function of volume so that I can actually do the integral. For that, I'm going to use the ideal gas law. I can solve this for pressure. Pressure is equal to nkBT divided by volume. And I think I'm going to use one more simplification after doing the substitution. So I have pressure is nkBT over volume times dV for the integral. And I'm never given a temperature, or in fact, I'm not given any of these quantities, N or T, separately. So what I think I should do is I should use this identity equation, the fact that initial pressure times initial volume was equal to nkBT, and throughout the entire isothermal process, the right-hand side doesn't change. So I can just replace it with this constant left-hand side. So if I do that substitution here, then the numerator simply becomes initial pressure, which I have, times the initial volume, which I have. So let's do the integral. Let me factor out the stuff that factors out of the integral. Pi times Vi. The integral of 1 over V is the natural log of V. It's one of the integral formulas you used to have memorized. Integrated from Vi to Vf, those are my limits. So just quickly working this portion out, it's technically ln V final minus ln V initial. With the help of the logarithm algebra, I can rewrite this natural log of V final divided by V initial. That makes things nicer because then I don't have to figure out what is the natural log of meter cubed. Meter cubed cancels out. So the answer here should be Pi times Vi times the natural log of V final divided by V initial. This should be the work done by guess. So let's write all this out. Let me just copy this over for the parameters. I just don't want to scroll back and forth. Or I guess I already had some of them here. So initial pressure times, this is initial volume would be 5 times 10 to the minus 4 times meter cubed times natural log of V final. I'm just gonna type in the part that won't cancel out. 17 divided by 5. 10 to the minus 4 meter cubed cancels out. So when I do that, I should get answer in joules, 64.25 joules. And it makes sense. The area here would definitely be smaller than area here. So 64.25. So 64.25, and as it's doing that work, it can afford to have no internal energy change, even though, you know, the first law says this, because there's a heat transfer, exactly enough to balance it out. That heat transfer is what makes the process isothermal, really. So, all right, so that's the process. Finally, physics demo called the fire syringe, where I love this. Based on the information you see in the photo. What? How much time do I have? 9 minutes. All right, I guess that's enough. So I gotta know the compression factor. So let's do this. You can just eyeball it. You know, it doesn't have to be very precise. So. So this is my work for C. Oops, that's not the color I wanted. The main thing I need to know is compression factor, ratio of V initial to V final. So, and I can use the ratio of the height of the column, I think, because the cross section probably remains constant. So let me get this as a measure of how high this final column here is, and I'm just gonna copy and paste it in. Here's one of it, two of it, three of it, five of it, 6 of it, maybe 6.5. Let's say 6.5. Yeah, 6.5. Close enough. So actually, 1, 2, 3, 4, 5, 5.5. So from this rough measurement, what I can say is that V initial divided by V final is about 5.5. So with that in mind, these are the equations that I need to use. The ideal gas law, PV is equal to NKBT. And in your textbook, there's an adiabatic process formula, which says this quantity is constant. P times V raised to gamma is constant. And you kind of have to know the expression for gamma. Or do I have it memorized? Information, so yeah, diatomic ideal gas. I want to say for diatomic gamma is 7 over 5, but I'm not 100% sure. So let me make use of the fact that this is an open book assessment. So I can look in the textbook to make sure that I remember the location of gamma correctly, and then I remember the gamma correctly. There's no shame in looking it up, just to be sure. It's been a while since I looked at it. I probably should have studied ahead to make sure I don't make mistakes and that I'll remember. It ought to be in the section adiabatic processes for ideal gas. And it should have this adiabatic expression. Yeah, all of that. Yeah, PV gamma is constant, good. And gamma is equal to what? It's not telling me what gamma is. Well, it's a Cp over Cv, so I can go look up the specific heat capacities of ideal gas. Heat capacities of an ideal gas. And I think there's either a table or something I can look up. So diatomic, Cp is 7 halves, yeah. Cv is 5 halves, so ratio 7 over 5, yeah. Good I should have trusted my memory. So with these equations in hand, this is what we can do. We can say so we are given the initial pressure, so P naught, 100 kilopascal times V is equal to N kb T initial, which will be 300 K. And now we work out the final expressions, P final, which we don't know, times V final, which we don't know, is equal to NKB T final, which we don't know. But this is where the adiabatic expression comes in. So what we can do is we can express we can so let me just do it the long way, not using any shortcuts. So we are trying to solve for T final. This is the one unknown we are trying to solve for, and we and this is an information we have from the picture. So as a first step in eliminating unknowns, we can eliminate V final by rewriting this as V final is equal to V initial divided by 5.5. So putting that in, I can have this expression P final times V initial, which for let's say V initial divided by 5.5 is equal to NKB T final. Still not good because we don't know V initial. Although we can figure out V initial from here, I guess, kinda. But what I want to do is more of I want to use the adiabatic process equation. So let's see. So let's write this out explicitly. Explicitly, it would look like P naught V naught gamma is equal to V initial gamma is equal to P final V final gamma. And from here, we could solve for P final. Yeah, so let's solve for P final, which will be P initial times V initial divided by V final raised to gamma. And this ratio I already know. It's 5.5. So it's a P naught times 5.5 raised to gamma. So I can plug in this P final into here, and I feel like I still have to deal with the V initial, but I think I can do it. So I think I'm doing this much longer way than I had to because I'm a little bit disorganized, but let's just finish it up within the time limit, and that's really what counts. So plugging in P final, it's a P naught times 5.5 raised to gamma times V initial divided by 5.5, so I can do gamma minus 1 in the powers is equal to nkb T final. And let me have this expression for V initial. V initial was nkb T initial divided by P initial. So I can plug that in. Oh, P initial cancels out, I think. Yeah, I don't even need a P initial. So plugging this in the whole equation, I have P naught times 5.5 raised to gamma minus 1 times V initial, and KB T naught divided by P naught is equal to N KB T final. Let's cancel out a whole bunch of stuff. N KB P naught, and that's it. T final is simply T initial times 5.5, the compression factor, raised to gamma minus 1. This might have been derived in the textbook. So, okay, so let's do this. 300 Kelvin raised to power times 5.5 raised to power of 7 over 5 minus 1. That should be 593 Kelvin. Yeah, that's hot enough to ignite paper or cotton or whatever that combustible material. I should have been watching time. That was supposed to be 5. I ran out of time while entering answer to C. It should have been 593 Kelvin. Come on. I'll bring the answer key over so that you can confirm that I was right. Sorry, I shouldn't have been so disorganized. Let me paste in my answers and then we'll be done here. I should have been watching time. I thought, I don't know. I saw that 9 minutes, and then I think after that, actually this doesn't work. After that, somehow I was stuck there. I didn't run the timer in my head, how much of the 9 minutes I spent. All right. Let's paste this in. And then, so I'll save work and continue. So I should have gotten, it's got 1, 2, 3, 4, 5, 6, 7, 8 parts, of which I got 6 right. So, I don't know, is that 3/4? 75%? Yeah, good. And let me go into instructor mode and bring in that screen so that I can show you the answer key for part C and demonstrate that yes, I didn't miss it. I just ran out of time to finish plugging in my answer. So test student, there it is. Yeah, correct, and here 593. Oh, why was it off? It might be a matter of this number being used. So I should have really just put in 590. That probably would have been graded as correct. So. Anyways, so that's it. So hopefully this is helpful. So a difference between part 1 and part 2, by the way, I think, yeah, it kind of tells you what chapters they mostly come from. So part 2 is usually going to have something that relates to heat engines. Part 1 may not. So with the part two, I've done a little bit of dice loading so that one question that you have seen me do in the past, I know I'm not gonna get that question. I kind of peeked at the question that's been scheduled to go in, and I made sure it wasn't the question I had before. So let me start. I still only have 20 minutes, and it's actually not a lot of time. If I don't, I'm not efficient in working through this, I can easily run out of time. Let me just start, and I should have full 20 minutes, I think. So let me just answer this properly, and then we'll end this portion of the demo. So it says, consider the thermodynamic processes shown on the figure below. This is the PV diagram. Denoted, okay. So I have these two parameters that are, I think, assumed to be known. Processes shown are for a monatomic ideal gas, okay. So monatomic means, it means a few things. One particular thing, degree of freedom is 3 translational degree of freedom. Okay. And image description, this is, it shouldn't give you any more info than what you see visually. It's an accessibility feature. Okay. With the process taking the path from C to B, okay, C to B, and then to A, okay, calculate the following. Work done by the system, change in internal energy, and net heat flow. So this is, it's almost, there's a kind of a standard strategy vibe to this thing, because there's a systematic way to approach this kind of PV diagram involved analysis questions. I will tell you some of the things that you should remember. You should remember the definition of work. Work is defined as, defined as this: pressure as a function of volume, integrated with respect to volume, from some initial to final state. In a simplest scenarios where you have constant pressure process, you might express this as pressure times the change in volume. This is one. And the other expression that you will use often is the first law of thermodynamics, which says the change of internal energy is the net heat transfer minus work done. And if this minus sign confuses you, just remember that physics convention is different from chemistry convention. Whenever we describe work, we're talking about work done by gas on system. So work done takes energy out of the system you're working with. And finally, you might have so this becomes important because this comes into the expression for change of internal energy. Change of internal energy is the degree of freedom. So in this case, 3/2, the number of particles times Boltzmann constant times the change of temperature. Or actually, I don't even need this change part. Internal energy is this if T is in kelvins. So as you look at these three equations, you can kind of tell which one is useful for what. This is useful for calculating work. This is useful for calculating internal energy. And this first law, it's often useful for calculating the heat because there's no other formula for heat. And finally, one final expression that you might be using is the ideal gas law. Pressure times volume is equal to NKBT. Here, the utility of the ideal gas law especially comes in because when you look at the question, it never gave you like a temperature. But internal energy is expressed in terms of temperature. You don't have temperature, what do? Well, you have this. So this NKBT, you can re-express it in terms of pressure and volume. So it would be like 3/2 times pressure times volume. So, so these are the common, these are the tools in your toolbox that you should keep in mind as you work through a question like this. So I'm gonna go through step by step, So let me draw the path for CBA so that I have something to kind of look at and have an intuitive feel for. So this is my pressure, volume, CBA. Okay. So for my work done, this is basically going to be the area under the curve, area under this curve. So this will be my work done. And that I can do it geometrically. I see this rectangle of height 2p naught width v naught. So this is gonna be 2p p naught times v naught. That's the area under the curve, which will give me the work done, and it's positive because it's positive area going from left to right. Change in total internal energy. So so if I'm looking for change, I'm looking for 3/2 times change of pressure times volume. I think I can calculate that. Let's see. So yeah, I can do it on the calculator, in fact. So let me have 3/2 first, and then I'm going to have the final pressure times final volume, which should be 2p naught times 2v naught, so 4 times p naught times v naught, minus the initial pressure and volume, p naught times v naught, p naught times v naught. And I don't think it really simplifies from here anyway. So that's change in energy. And for net heat transfer, what I do is I solve this first law equation for, can I do this on the right? Yeah. Let me solve this for net heat. It's going to be change in internal energy plus the work done. So I have both of them up here, so just add them together. Copy this. And I'm doing this in a lazy way. I mean, so, you know, sometimes there are expressions where if you try to simplify it, you get something beautiful. Here, to the way the system grades this, they grade it by numerical equivalence. They plug in some random numbers into these variables and see if the number you get is the same. So if you have a complicated expression, doesn't matter because the way system evaluates it, it doesn't take complexity of the expression into account. Just checking the time. Okay, got 30 minutes left. So each of the quantities above may be positive or negative depending on the process. Briefly describe in your word what these signs mean for. Okay, so for work, positive means work done by the system on the surrounding. Negative means work done by the surrounding on the system. Delta E, positive means increasing internal energy, temperature. Negative means decreasing internal energy. It's fine without that. Q, net heat transfer. Positive means net heat transfer into the system. Negative means net heat transfer out of the system into the surrounding. I think that's all it's looking for. So, okay, those are the answers. And for the process, taking the path from C to A along the path C to A, okay. So let me just copy that over so that I don't have to keep scrolling up and down. So, so I'm working on B, let me C, in the PV diagram, I have these vortices. Oh, I didn't draw it right, that's fine. So C to A, directly connecting. Assume that the work done is the 3/4 of the work done that we calculated above, which was that. So let me just write that down. So what the question is telling us we can assume is that assume that this area for the work done is 3/4 of that. So 3/2 P naught V naught. Okay, in the process, yeah, calculate the following change in the internal energy. That's exactly the same. Didn't change because internal energy is a state function. What state function means is as long as your endpoints are the same, nothing's changed. So as much as the phrase state function bothers me, it shouldn't really bother me so much because it is a useful problem solving tool. So for the net heat transfer, I'm actually using the exact same expression we derived above. Change in internal energy, which didn't change, plus the work done, which is now different. So now I use that different amount of work done for the change for the heat transfer. So the amount of heat transfer is different because because both the work done and heat transfer are path dependent. They are not state functions. Find the path from state A to state C, then minimize the heat flow out of the gas. Explain the space below, how this path minimizes the heat flow, and if possible, calculate the amount of this minimize the heat flow. Okay. So you can answer it a couple different ways. How much? I have 10 minutes. Okay, so I have some time to waste. So let me explain it this way. Label B and D. So I'll just type it out, my thought process. So if we are limited to the path shown, then the path then minimizes, A to C, minimizes heat flow is one that minimizes absolute value of work done, because the net heat flow is equal to change in the internal energy plus work done. Plus work done. Wait, let me just think this through. Heat flow is the one that minimizes. So work is gonna, so going from here to here, work will be done on the system. So W will be negative. If W is negative, I don't know if I want to minimize. Let me think of this through. So because this is that, to one that maximizes. The one that makes W as negative as possible. Is that right? Huh. Because I had a different process in mind. Heat flow out of the gas. No, I'm confusing myself here, because the one that makes no, as small as possible, because QNet, which can be confusing, or in terms of absolute valued quantities, it's going to be minus absolute value of QNet, because it will be heat flow out. So the QNet will be a negative quantity. That is equal to delta E internal, which will be negative quantity. So it will be absolute value of this, that. And then the work done will be also negative, so it'll be minus work done. So if you are looking at in terms of what's the absolute value of heat transfer, it's going to be absolute value of heat transfer will be, delta E int plus absolute value of W. Okay. My intuition was telling me what I was saying before was just not right. So this portion you can change. As long as your endpoints are the same, this is not going to change. So the only part you can change is the amount of work done. So how small can you make this to be? Well, so this is where it kind of depends on your creativity. So let me actually reword this. So let me start with this. The path that minimizes heat flow is one that makes that small as possible. So how small can we make this, which will make this smaller? How small can we make the absolute value of the work, which will make the absolute value of heat transfer smaller? So this is where if we are restricted to the path shown, then it should be A to D to C, because this will minimize the area under the curve to this, which is the minimum you could have with the path as shown, in order to minimize the area under the curve. And you could do this, calculate the amount of this minimized heat flow totally fine. You can go ahead and do it. And this being kind of an open-ended question, you can also answer with a little bit of creativity, which could be something like this. If we are not restricted to the path shown, then theoretically, it's possible to make absolute value of W 0, mathematically the smallest value possible for an absolute value. To do this, from A, we would go all the way down to 0 pressure at temperature equals 0 Kelvin. And at this 0 pressure, we would change volume from V naught to 2V naught, doing no work. And at the volume of V naught, we raise the pressure up to P naught at a finite non-zero temperature. And there's a heat transfer out here, nothing of any kind here. Heat transfer in, as you go back up to C, up to P naught at the point to C. This path minimizes work to 0, so it minimizes net heat transfer to basically what you must have, change in the internal energy. Yeah. So that's another answer. I don't know if I mentioned this in model answer or not. It's sometimes I don't know. And the question didn't specify that the path that minimizes heat flow must be one that's shown. So okay, with that, I have 3 minutes, so let me use that time to attach my work, and then we'll submit an end. And again, my recommendation for you is to take some time to organize your work. Don't try to do it within the time limit. There's no extra prize for doing it within the time limit. The system does timestamp what you submit, so I guess the only thing where I would hang up is if after I've graded it, then people change their work. Like, don't do that; it's annoying. But otherwise, I don't really care too much about at what time your work was submitted or last changed. Okay, let me submit it then. So here I should still get some points from these if what I entered is right. And I think what I entered is right. Yeah, let's hope. Submit and end. Yeah, I already attached the work, but you can also do it here after time limit has run out. Okay, I've got some points. So how many boxes are there? 1, 2, 3, 4, 5, 6, 7. So I should have gotten 1, 2, 3, 4, 5 out of 7. Let's see. I'm just curious. Did I get 5 out of 7? Yeah, I got 5 out of 7. Good. So all the expressions I entered are correct. And these, so after you submit, after the due date, you will have access to answer key. You can kind of take a look, see what you got, see what you missed. And after some time, we'll also have the group review of timed assessments.